My name is Paul Bannahan, and I'm the Artificial Intelligence Research Fellow in the Mater Misericordiae University Hospital. You might know it better as the Mater Public Hospital in North County Dublin. Thank you. My talk is about coding on the healthcare frontline, developing medical imaging AI from within the Irish hospital system. So just a little bit about myself, because I do get asked this regularly enough of what's my background. My background is primarily engineering. I have an electronics degree from DIT. When I finished in DIT, I moved into doing several different startups with different levels of success. So a lot of my work in there was around minimal viable product development and design and building proof of concepts for public and private sector entities. After I kind of did a lot of work in that, I moved to go into something around computer vision. So a lot of my work in my startups was based around computer vision applications and image processing. So it was kind of natural to move into a master's that did computer vision as one of its majoring areas. So DCU provides that. And my title for my thesis was actually Deep Learning for Biomedical Image Segmentation using Cardiomitochondria. So cardiomitochondria are small microscopic components of cells, and what the purpose of the project was to locate those cells and quantify them, because that is a measure used in quite a lot of kind of biomedical applications within a hospital to determine certain different pathologies within patients. So in August 2021, I started in the Mater Hospital in my title, in my very fancy title. But prior to that, I don't really have a clinical background. My background is engineering, it is development, it is providing solutions for key stakeholders. So just about hospitals in general, the pandemic is still very much part of our day-to-day life. Masks are still part of the everyday norm. Social distancing is very much present in every aspect of the hospital. So the presentation I have for you today is kind of broken into 2 or 3 sections, depending on how you look at it. One's an introduction to radiology, so that I can give you context for how my research is being performed and how it works. And then I'll go into the clinical measurements and how I've been using Python to do those kinds of those calculations for clinicians. And then into the more interesting work that I've spent quite a lot of time on over the last couple of months, the deep learning and the artificial intelligence applications within radiology. What's radiology? Radiology is a medical specialty that focuses on the diagnosis of patients through medical imaging. So we can diagnose and manage patients' prognoses and pathologies through medical imaging. It's non-invasive, and it is kind of the way that most people will interact with a hospital at certain stages of their life. So the image here is actually of a reporting room. So a reporting room, you might have been in a hospital and noticed a very dark room with people working and staring at screens. The reporting room is for radiologists to be able to work and to diagnose and to read these images and report them in a timely manner and in an effective manner. So this image is actually from Leeds, because when I took a photo of the one in the Mater, my phone auto-corrected the brightness. So all of these rooms are slightly dull, very high quality screens, and they allow people to perform their work effectively. So this is also a teaching hospital. The Mater is a teaching hospital, and so is the photo here, where trainee radiologists or registrars are present and can discuss complex cases with each other to ensure that they've not kind of missed any issues. And consultants then, the fully trained radiologists, will then read those images again to double check those in teaching hospitals. So just a breakdown of what happens in the Mater on an annual basis, roughly. So this is the breakdown of the work that goes through a hospital. Nearly 150,000 scans were done in 2021 in the middle of a pandemic. Most of those were X-rays, then CTs. They're very vital as part of the general healthcare flow, the workflow nowadays. The image on top here is a CT scanner, and the one below is an X-ray machine. So who works in the radiology department? There's quite a broad spectrum of individuals, from fully trained radiologists to registrars who are trainee radiologists, who are doctors who are specialising, and then radiographers who take the scans, the students who are present in the hospital to get their necessary experience, medical physicists, who I'll be discussing a little bit later on, nursing and healthcare assistants, administration, portering staff, and clinical engineering. Possibly AI and application developers will be a part of radiology in the future, purely as a way of actually engaging properly with those key stakeholders. The development of the work that I've done, that I'll be discussing in a few minutes, wouldn't have been possible without me being based directly in the hospital. The amount of feedback I would need and the amount of kind of information present is or amount of information that I'd need to know and learn is quite large. These people train for 12 or more years to become a full radiologist, so being in the environment with them provides me with a lot of kind of context for what's going on. So some of the imaging modalities that are present in the matter, a modality is just a machine, effectively. A CT is a modality, an MRI is a modality as well. So in the total, there's about 14 modalities in the Mater Hospital. X-ray, MRI, CT, ultrasound are very common ones that you would have heard of. PET is positron emission tomography and is typically used for the monitoring of growths of cancers and determining to what extent cancer has kind of evolved over a patient's treatment. For X-ray CTs, radiation, they use radiation. That source of radiation is from the machine itself. But for nuclear medicine, it's a little bit different in that the source of radiation is given to the patient. So the patient receives a small dose of radiation, and then a device called a gamma camera performs an actual analysis to capture that detail back. So this individual, the black nodules are what we're looking for, and that shows actual growths and cancerous growths within that individual. On a normal person, that would be very well distributed across. In the PET image, just above the top of the lung, here is a very bright spot, and that is actually a tumour within that patient. So you can see why these are so valuable. We don't need to perform surgery. We can actually analyse these patients relatively easily without giving them any extra conditions to be worried about. So my research is around CT and MRI. So I'm going to briefly introduce you to CT and MRI and the differences between the two, because even people who I work with in my project on a daily basis ask me what the differences are regularly. So CT is effectively an X-ray tube that moves around the body, and there's a video here. Hopefully it won't be very loud when I play it. And this is effectively how they work. So this is a CT, as you probably wouldn't have seen it, with the hood off, so the protective cover is removed while they're doing a test. This goes quite fast, it's quite loud, with the average scan taking about 10 to 20 minutes, depending on what you're actually looking for. There are safety concerns, naturally, with this. So there's concerns over the radiation dose exposures for patients, burns can ensue, and also radiation sickness as well. But in total, in general, CTs are very common. 30,000 of them were done in the Mater Hospital only last year. So you may have also heard of CAT scans. CAT is the same thing as CT. They're just an older name for that kind of technology. So they're very similar. If you hear somebody asking for a CAT scan, they're asking for a CT. So when the X-ray tube moves around the patient, we do see, get a different response in the signals that come back, and as a result, we can determine the types of tissue. So this is the X-ray image, or the X-ray. Oh, sorry, I don't have a laser thing on. So this is the source of the X-rays going through the patient, and this is the signal that will come back. Now, the images that are generated are this kind of bizarre-looking object over here called a sinogram. Now, there are several dozen different equations per manufacturer of how those equations work on that data, and they pull out different types of images depending on what we need for a different patient. So one CT scan can have dozens of different reconstructions performed, and as a result, we can have different series of images produced. And those series are produced based on what that patient will need at any different time. So those algorithms are also kind of specific to what they're looking for, but also different manufacturers have similar ones, but not wholly the same. So an example of the an example of the PET CT scanner in the Mater Hospital. This is typically used for monitoring of cancer. So it's a PET CT, so it's a PET scanner and a CT scanner in the same machine, so that we can overlay those two scans so they're exactly identical. So this is kind of the control room that you might see occasionally as well. So this room, you might be wondering why the glass is kind of tinted yellow, and that's because it's lead lined. Everything in these rooms is lead lined, the floors, the walls, the windows, everything. So the patient will receive a small dose of radiation, but the radiographer, the people who are taking those scans, will get that dose and every other dose for that day, unless there's these protection mechanisms in place. So over the course of their shift, over the course of their week, over the course of their career, they would get a large dose of radiation. And that can be concerning. So there are legal precautions in place and legal standards adhered to ensure that that's not a continuing issue. So all the modalities that use any kind of radiation use lead-lined walls to some degree. If you are in one of those rooms, you will see a little plaque that says how much lead is in the wall around them. But typically, they're there for the safety of the staff. The scan is actually done with set up using these two screens down here, and then they can monitor and watch the scan be taking place and can respond to the patient as needed. So that was CT. This is MRI. MRI is a lot different, quite honestly. It uses an incredibly powerful magnetic field that when you are near it, it will realign the atoms within your own body. And it's quite intricate how it works by times. So what it does is it sends when all of your atoms have been realigned, it sends a pulse through the scanner, through the magnetic field, and it causes all of your atoms to flicker. That response of your atoms to return back to that original position is what we're measuring. Depending on how we change that initial alignment of those atoms, we can read images back slightly differently, again, based on what is needed for that given patient. So the average scan for these images, for MRI, is quite a lot longer. It's about 30 to 45 minutes. There are some applications that are like artificial intelligence trying to make that faster. But again, it's kind of one of those things that won't be happening immediately, but people are trying it in the background to make it work a little bit better and to be less kind of time consuming. So the strength of the magnetic field is exponentially powerful. So at the distance you might be at like 10 feet away, half a foot nearer, and be much more powerful and is quite a dangerous thing. But more on that in a moment. So here are some of the examples of the images. So depending on how we change that magnetic field in the first place, we get different images back. They highlight different features and attributes of that patient, and that's kind of what these radiologists would be looking for. So depending on what exactly the patient came in for, if they came in with a stroke, they might get a different series or more of that particular series to actually be able to diagnose that patient. So it's very similar to CT in that regard. And then FLAIR, so T1 and T2 is the way that we change the atoms, and then FLAIR is called fluid attenuated inversion recovery. And I'm not comfortable discussing that at length. When we get into MRI, it's very much down to subatomic physics and how all of those kind of attributes would work in line with each other. So safety of MRI is absolutely paramount. I did mention on one line how CTs can have radiation exposures and dangers over that. MRIs are a lot more immediate in their danger because they will just pull metal towards them without care. There's several cases every so often in the States where a police officer moves into an MRI machine or into the room of the scanner and it pulls the gun out of their hands. I don't know why they keep doing this. This is a continuous thing. I'd love to know why they're doing it. Everybody goes through metal detectors and is tested and is asked and repeatedly. Nope, they just walk in with it. So other accidents can happen. The object here is actually, I believe, a motorized wheelchair that is not MRI safe. You notice that the MRI safe wheelchair is not a problem here, but it has ripped up the floorboards and moved the 200 or 300 kilo bed that is designed to take a lot of weight and just destroyed it and moved it across the room. MRIs are very valuable. They're very necessary. This will destroy the machine or put it down for a long period of time. So please don't do that. That's basically the thing to take away from that slide. So briefly, just the difference between CT and MRI. CT uses ionizing radiation, MRIs use magnetic fields. CT is much faster, but MRI works better for soft tissue. So things like the brain, MRI is kind of the more appropriate use in that. So sources of noise in the images can be the finite amount of radiation present in CT or slight imperfections in how the magnetic field is kind of built and designed, because we can't make these magnetic fields perfect in general. So we're starting to move towards the Python element of this talk, but first I have to introduce image quality assessments and medical physicists. Medical physicists are physicists that work around the application of radiation therapies, quality assurances for CT scanners and X-ray machines, and they are legally protected clinical staff members within hospitals. They are vital for the implementation of these safety protocols and are the radiation protection advisors of most hospitals. So when they're doing a quality assessment of a modality, they will look at three main characteristics: noise, spatial resolution, and contrast. Noise and contrast, they can produce obstructions to pathologies like lesions, tumours and fractures, and we can't have that. So we try and reduce those characteristics and their kind of effect on a patient image. And then spatial resolution is to try and ensure that the scanners are capable of seeing the smallest parts of a patient's body so that we can be comfortable and reliable with what we're trying to do. And the assessment tools that they use for this are things like anatomical phantoms, where it's meant to look very human or meant to mimic part of human anatomy. And I have an example on the next slide where it's kind of a human head, but it's not fully, but more on that in a moment. Targets are similar enough to anatomical phantoms, but they're more along the lines of very high quality metal, particular types of metal. So one's called an MTF target, and what they're doing is trying to determine the spatial resolution of those objects back. And then custom software solutions is something that they've been trying to move towards over the last 10 or 20 years, roughly. So those solutions are very common in the Mater hospital, but other hospitals have their own mechanisms of doing things. They're typically written in MATLAB, but there's been a big push over the last few years to move them to Python, with more Python applications being made over the last few years. And even the things that are made in MATLAB being moved to Python because it just works better and it's much easier to actually interpret later on for when somebody moves into another role and isn't available at that time. So here's one of the head phantoms. This is a head phantom from Mullingar Hospital. So this is to mimic a human head. There's a fake skull put into it, surrounded by a kind of uniform jelly substance. That is used to kind of determine the noise characteristics of the scan. It's not overly used, being perfectly honest, but I wanted to include it here because it is a good example of the power of CT and the precision of their reconstructions. So we can reconstruct a scan into 3 dimensions, and that is incredibly accurate, because even now when patients are getting scans wearing masks, we can tell the impression of the elastic on their face from the CT scan. We even see the bar, the metal piece of across the nose, bridge of the nose. We can see that in the CT scan in fairly high detail. So it's just an example to show you what CTs are capable of. Data accessing and management in hospitals is complicated. So here is the best way to describe it is to actually give you a diagram of it. So it's called a PACS system, or Picture Archiving Communication System, and it's for the storage and management of that data within a radiology department or within a hospital in general. It allows the flow of that data to who needs it, and to the radiologists who need to report on it. Those reports are held within that structure as well, and are available to other clinicians outside of the radiology department. The PACS system in a lot of public hospitals in Ireland is the same one. It's called NIMIS, which is the National Integrated Medical Imaging System. This is unique to Ireland in that most other countries don't have this one provider of PACS systems. So it means, but it does allow that a patient that has had a scan in, we'll say, Limerick, to have that scan seen and read again in Dublin. So that happens occasionally when patients have to be transferred and things. So it allows for a degree of comfort when reading those scans. It also means that if you've a scan from a few years ago and you have an accident tomorrow, you will be able to have that scan from previously read, as well as your current one, to see the actual the changes in your anatomy and the pathologies that are present within your body. So it is a very helpful tool, not only for you, but for radiologists to actually determine, is this an issue or is it something that's not pressing at the moment? So now, what are medical images? Medical images are actually something called DICOMs. DICOM is digital imaging communication over medicine. They're not your average image. They actually contain not only the images themselves, the pixel values, but also a set of headers. Those headers can be the patient's name, date of birth, age, the locations of the hospital, and then things very specific to the actual images themselves around like the radiation dose in CT that a patient may have received, and is very much to make sure that if those images get lost or only one image is found, that we know who they relate to, so nobody's data is lost. The data ranges for CT and MRI are also very untypical of normal images. So anyone who isn't aware, normal images that you would see are typically between 0 and 255 pixel values, or grayscale values. But for CT and MRI, it's quite a lot more, quite a significant amount more. And this is for a few reasons. So these images here we can only see 256 levels of grey, but what we do is if we can move that kind of window across that line from minus 1024 to 3000, we can change the things that we're highlighting. So this window over here, as a window is what that terminology is called, this window here is actually to highlight structures within the lungs. The one in the middle is for soft tissue, and then the one on the end is for bone. They highlight certain characteristics more. I know some clinical staff don't see the differences, but it is there. It is part of the training for radiologists to actually see different aspects of it. Typically, the thickness of the slices through a patient, or the number of images, is between 1 millimeter and 5 millimeters for CT. So we can imagine that the scan going through the patient's body, we have 1 millimeter images all the way through, and to quite a high level of accuracy, as I mentioned earlier. So here are some of the tools that are used in radiology in general. There's PyDICOM, Python Medical Physics, which is for planning of radiotherapy applications. NumPy and Pandas are very typical. I don't think I've written any code in the last year and a bit, that doesn't include them to some extent, because Excel sheets are very easy for clinicians to understand and to grasp, and I'm quite happy to use. And then NI-Babel. So I mentioned what DICOMs are. NI-Babel works with something that's similar to DICOMs, but doesn't have as much patient data. They're called NIfTY files, which is a neuroimaging file format. So PyDICOM is the main library that I've been using for handling these DICOM images. It is specifically designed to work with this, hence the name. So we can read in an image with its headers, or we can read in a DICOM with its image and its headers, and we can analyze it relatively easily using PyDICOM. Now, there's only really one line of code in my entire presentation, and it is that one line for a very good reason. If you read in images and they're not in the correct order, they're not really useful for a lot of things. So Python thankfully handles this very easily by just using a lambda function and sorting the list of images appropriately. If they're not in the correct order, as was an issue with my own project only a few months ago, the clinical measurements that you're doing are unreliable and can't really be used. I know it was a significant issue for quite a while. Then the Hounsfield unit transformation is mentioned here. So in CT, the pixel values are typically 0 to 3000 or so in the DICOM, but that's not the correct scale. So we actually have to put a transformation into it to move them back into the correct range. And again, this is handled automatically by a lot of software in the hospital, but if you're handling these in Python manually on your own, you will need to do this. There's a lot of implementations of it available online, though. So This brings me to kind of why I'm in the hospital at all, and that's the MedEye project. The MedEye project is an Enterprise Ireland-backed Disruptive Technology Innovations Fund initiative, and it is the project's goal is to develop a platform to aid with the implementation of AI applications within a clinical setting. So there is no way of doing that really easily in the hospital at the moment. There are AI applications running in the Mater Hospital at the moment, but it's a very long process to get them there, and it's not straightforward. So MedEye is aiming to actually resolve that major issue. So two of the main use cases that we've been working on are carotid artery calcification, which I'll discuss in a moment, and then my own work, which is this image translation project, which is conversion of CT to MRI images, hence why I'm after spending a few minutes going through those two different modalities. So there's 6 main partners in the project. There's Mater Misericordia University Hospital, UCD, Meritive, which is formerly IBM Watson Health and was recently renamed, Dundalk IT, Novalia and Davra. Novalia and Davra are 2 startups and private companies that are working in conjunction with the rest of us to kind of resolve the issue here. So carotid artery calcification was my original workflow about this time last year. So the carotid arteries are based in the neck, both sides of your neck. So you have a left and a right, and then you also have a left and right, internal and external. So halfway up your neck, the carotid artery splits into internal and external. Internal feeds your brain, and external feeds the rest of your head. But over the course of your life, plaque can build up in the walls of the artery, and as a result, that can be a considerable factor around strokes, heart attacks, and other major adverse cardiovascular events, or MACE. So this patient here came in for a CT scan, and I went through and annotated out the calcification here. So this is the carotid artery calcification in that image here, and this there, and those over here. So there's 3 different image types here. There's axial, sagittal, and coronal. And axial is basically the scan from head to feet. Sagittal is left to right, I believe, or it's right to left, I can never remember. And coronal is front to back. So with scanning somebody in 3D, we have that data is reconstructed in that way so we can analyze it correctly. So different patients will have that kind of, again, depending on why you go to the hospital, you will be kind of reported on in a different way, depending on what's needed. So medical imaging annotation is how I did all of that. So the 2 main tools I used were ITK Snap and MedSeg, and MedSeg was designed for and by radiologists, and ITK Snap is a more broad medical imaging annotation software package. So all the pixels relating to carotid artery calcification are labeled throughout every patient in a data set that I gathered. That data set is about 500 patients in total size, and a lot of people say that that's not very large. It's over 250,000 images. It is 80 gigs or something in total size, and I've annotated every single one of those patients for this carotid artery calcification. So the clinical measurement that we were using is called Agatston score. Agatston is around since 1990 and is a quantification mechanism that clinicians are very comfortable with, and it allows the actual determination of how kind of severe a patient's arteries are blocked, and kind of management of that patient's pathology afterwards is kind of performed. So the process of actually doing those clinical measurements was all completely through Python once the annotations were completed. So here is actually an example of that annotation of a patient. This patient is a 90-year-old male, and you can actually see the carotid arteries are quite heavily calcified. So the program basically reads in patient's images, it organizes them with that line of code that I showed you earlier on to make sure everything is in the correct order, and it applies the Hounsfield unit transformation to every single image before any calculations are done. And that makes sure that it's in the right lines within clinical estimates. So the Agatston score is not my favorite clinical measurement because it's based on not the best technology. So at the time when Agatston and his colleagues were writing the paper, the smallest slice that you could do on a CT scanner was about 3 millimeters. Now it's sub-millimeter. Typically 1 millimeter slices is what we're using. So we can be more accurate than Agatston was, but 3 millimeter slices is what this software has to report on. So we take every third slice, as Agatston was doing as well. So those calculations are based on the Hounsfield units. The Hounsfield unit is basically a measure of radio density of a patient. CTs are measurements of radio density in general. So that is calculated for every slice, then that is summed up for every patient, and then we move on to the next patient. The packages that were key to that are naturally PyDicom, NI Babel, which is used for the annotations, because all the annotations came back in a nifty file format, and of course Pandas, everyone's favorite. So moving more into kind of my own research work now. So artificial intelligence in radiology is becoming more and more common and more accepted as well. Typical applications are like stroke and fracture detection, prioritization of the work list. So an AI will work in the background and read an image and determine if it needs to be moved up or down on the actual work list priorities. So if you have a fracture in your wrist, compared to somebody who has a hemorrhage in the brain, there's slight different management processes in place. Clinical measurements, as I just showed you, and also opportunistic insights. So opportunistic insights is where a patient comes in, say, for a scan of the neck, but we can do the Agassiz scoring, the carotid artery calcification scoring at the same time. So those are models that will run in the background to actually gather that information and provide it to clinicians so that they can include it if they need to, or just leave it as it is, depending on what is going on. Some newer applications, so these are the applications that I'm kind of working on quite a lot at the moment. Generative adversarial networks, or GANs, for the development of a tool for the Mater Hospital. So I do have more slides on that in just a moment. CES is quad equina syndrome. Essentially, the patient presents with a herniated disc or slip disc, and it can cause significant and permanent damage. So we would like to analyze that better in time and more readily. And then, as I mentioned, I actually work in medical physics at the moment, and they're trying to automate their QA process to make it a little bit more accessible and reliable and quantitative, not qualitative. Just a couple of misconceptions as well around artificial intelligence in clinical settings in general. We're not trying to replace clinicians, and we're not trying to replace modalities. We're not, like, radiologists can't be replaced by an AI or a series of AI. It's just not going to work. It's not feasible, it's not practical, and it's not in the best interest of patients. And everything in hospitals kind of comes back to the best interests for patients in a general setting. Also, so during the pandemic, many people worked on like COVID-19 AI applications, and they were not the best at doing their own jobs. There was a paper a few months ago that reviewed several hundred other papers and their implementations and how they worked, and they found about 2 or 3 of those models and those processes were potentially valuable in a clinical environment because of the way that the data flow works. So the main work that I would get comes from clinical staff. It's not me deciding something, it is them that ask a question and we go and do an investigation over it. The Quad Equina project comes from radiologists, and they're very keen about seeing the applications and the benefits for different patients as well from that. This is the Quad Equina project. So the official title for the project is CT to MRI image-to-image translation using generative adversarial networks in out-of-hour emergencies imaging for Quad Equina syndrome. So we can see a normal and an abnormal image of the spine, and the normal image, this is the spinal canal here where the cursor is, I hope you can see that, and there's no obstructions within the spinal canal. But within the abnormal, where the patient does have the quad equina, their disc has herniated and is cutting off their nerves. This can lead to permanent damage and is incredibly painful for patients. So there was a question by some of our registrar radiologists about, can we use a CT to diagnose this, and would the people who are doing the surgeries be comfortable with the CT over the MRI? The answer is no, purely because they're not trained to see the CT the same way that a radiologist is. They're used to seeing an MRI, which is quite distinct. This is a problem. This needs to be fixed. We'll do it. But the CT is a little bit more subtle about what it's doing, but the data is there. So two of the registrar radiologists, Philip Dempsey and David Ryan, decided, let's see if we can play with the settings of CT images to actually perform this. So this has been an ongoing study of theirs in the hospital for the last 2 years, where they're consenting patients actively to get involved in doing this work and to see if there's any kind of applications for them for these kind of CT images. In general, surgeons aren't happy with it because they're just not comfortable with CT data. This project is specifically for out-of-hour work. So mostly because MRIs are a scarce resource in Ireland outside of normal working hours, about 4 or 5 p.m. And there's only really one 24-hour MRI centre in the country. It's the Mater Hospital. And that's because the Mater is the national spinal centre. So patients with suspected spinal issues are sent to the Mater for the surgery because the specialists are there and the teams are capable of kind of handling those issues. Patients out of hours are typically transported in the middle of the night. A case a few weeks ago, a patient was transported at 1 a.m. from Limerick in an ambulance throughout the night to arrive in the hospital. That's quite expensive. It's quite resource intensive, and it's not always necessary for the patient, but also the patient doesn't necessarily get the MRI, even though they travelled a few hundred kilometres for it. So some patients may have a pacemaker, and as a result, they can't get the MRI scan because the cardiologists and the other clinicians aren't available for them. So that's kind of an issue that this project hopes to kind of resolve by providing an AI tool that gives a bit more kind of context to those CTs for those surgeons. There's no paper about this just yet, or there's no publications in general. Hopefully in the next couple of weeks and months, I'll be able to do more experiments and have that paper prepared. So you're getting a little bit of a sneak peek today, I suppose. So what do the results of my project look like at the moment? Quite good, relatively. The CT, this is the CT that Philip and David have developed, and it is quite high quality. This patient does not have quad-equina syndrome. They do not have a herniated disc. The pathology in this patient is okay. They don't have a spinal emergency. So the predicted MRI from my AI is here in the middle of the slide, and it corresponds quite well to the actual MRI taken on within a few hours of the original CT. So the data set that was used for this project is incredibly heavily curated. It's about 50 patients in total, and is really only available in the Mater Hospital because it's the National Spinal Centre and because of quite a lot of other attributes that are just not feasible in other hospitals. So all of the patients were fully consented for this project. The CT is a little bit higher radiation dose, relatively, so they're all informed about what's going on with this project and what the end goals are of this. The results here, in general, look very, very closely very close to the actual MRI, and that's because the AI models that we've developed have actually determined that the data is present within the CT image. So the nerve endings here, the quad-equina nerves in the predicted CT are present in the actual MRI, and that's kind of the key thing here that we're interested in. The general structures are all present, the discs between the bones are accurate, and actually the feedback from many of the radiologists has been incredibly positive, with even the trainee radiologists being quite taken with how precise this is. So they've seen results with patients with quad-equina and without, and they're interested in both applications and both details. This is, I think, the second time that we've shown these images publicly. The first one was at the Royal College of Surgeons annual scientific meeting for the Faculty of Radiology, where we did a poster presentation, and there was a lot of people stopping to go over this particular image set, because they're very taken with how precise it is. And it is there. As I mentioned, the data is there in the CT. It's just convincing other clinicians that that is there in the MRI. So there are other providers of, there are actual companies set up to be providers of artificial intelligence tools in radiology. There's Glimmer, who work on bone fracture detections in X-ray. So X-rays in the Mater Hospital were about half of the workflow in 2021. AI Doc produce large suites of AI applications, so they're kind of a catch-all for different application types. And then we have Rapid AI. Rapid AI is implemented in the Mater Hospital for a few years now, and they're actually working on hemorrhage detection specifically for stroke patients. So their AI works to actually see if a patient has sustained significant damage over time with those injuries. So a couple of problems with clinical implementations of AI, quite naturally, is the data access and the data quality. Getting good data in radiology is quite difficult. One of the issues with COVID-19 AIs was the data was open source, wasn't really clean and wasn't reliable wholly, with a lot of them just saying, this is COVID-19, written onto those images, which means that the model probably just learned to read the actual image literally. So we need radiologists to be a part of this, and clinicians in general. So the images from the CT to MRI project, not only do we need radiologists to actually get those images and to consent the patients and to be willing to move forward with that project, we needed a radiologist to perfectly pair those images, the CT and the MRI, so that they overlap perfectly. Not an easy process for even clinicians with more than 20 years experience. It is a very slow process to do. So 50 patients will take a considerable amount of time to actually fully label and annotate. The implementation of AI in clinical settings is just not there. Hospital infrastructures are not designed for this. They're not designed for data accessing in massive quantities. It's specifically for one patient at a time. If you request your images, we can give you your images. But if you're looking for the 500 patients from my carotid artery calcification data set, that took, I think, 10 weeks to download, because I'm downloading them one at a time, and it's about 10 minutes per patient. Not the most enjoyable experience in the hospital, I'll be honest. Then the reliability factor of AI is a significant kind of worry. If an AI doesn't work, if it breaks, if it predicts the wrong thing, is there ways to catch it? And is there ways to manage that problem? With CT MRI, we can do that. It doesn't look correct. We have the CT, we have the synthetic MRI, we can see if they align correctly or not. For other things, we have a bit of a problem with that. GDPR is also a concern, and it's naturally that patient data is very sensitive. So here are just a few conclusions from the talk today, getting towards the end of my presentation now. So briefly, there are a lot of different modalities present within different hospitals. All of those modalities use DICOMs. It is an internationally recognized standard that those machines and modalities produce those kinds of images. Python is becoming more widely used and more widely trusted in deep learning applications, and also in like medical physics applications as well. Depending on where you go, that might not always be the case, but there is a general trend towards using Python in those applications. Clinically, we're trying to implement those things, but implementation of any of these mechanisms is quite a long process, and we're slowly making our way through it. And deep learning, as I mentioned, all radiologists that I've spoken to are quite interested and quite accepting of the results of those AIs so far. And it's going to be interesting working with them over the next few weeks. One major thing I do want to have people take away today is the use cases come from clinical staff. They do not come from technical staff. They're solely coming from them of, I need help with this. This is what I need to do. The last thing is just a couple of resources here. PyDICOM, there's just a link to PyDICOM in general. The paper there, this is the Generative Adversarial Networks, a primer for radiologists, is a paper and a presentation done for and by radiologists and given at the Radiological Society of North America's annual meeting a few years ago, and is kind of a very good paper if you're interested in reading through it. It does explain GANs and things like that in good detail. And then finally, Kaggle is a good place if you are interested to get started. Data sets are present. There's competitions as well. There's one only ending a few days ago from RSNA, the Radiological Society of North America, and also just general exposure to medical imaging. So with that, that's me finished. So I'll leave you with two photos from the Mater Hospital. One is the Misericordia building here, and the other is the photo of radiology in the Mater at the moment. So Radiology is present here in the middle of the image. It's the middle floor. Above us is ICU. Below us is A&E inpatient clinics, and below that again, down here by the trees, is the emergency department. And that means the radiology is in the middle of all of the main flows of work, so that they can be effective in how they manage their day and manage the workflow for patients. Thank you so much, and I hope you enjoy the rest of your day.